Hello and welcome students. Today we are going to discuss a new topic, that is distribution of shearing stress over a rectangular section. In yesterday's session we have discussed about the generalized equation of shear stress, that is tau is equal to Fa y bar upon Ib. That is, you can see on the equation tau is equal to Fa y bar upon Ib. Now you can see the figure, the rectangular beam as it is. This is the neutral axis at which the tau should be maximum. Now how this tau should be maximum, that also we will prove in today's session. Consider one strip. This is the strip ADJK. Okay, this strip is at a distance of y meter from the neutral axis. Width of the rectangular section is B and the depth of the rectangular section is D. This is the layer BC at the bottom. Now we have to find the stresses, shear stresses layer by layer. At the top layer it will be 0, at the bottom layer it will be 0. How it is 0? So this axis, you can see in the figure, this axis is considered as y-axis and the right side of this axis are the values of shear stresses. So at this point, top fiber and bottom fiber, the value of shear stress is itself 0. Going down, at the layer JK, the stress will be tau. At the layer neutral axis, the stress will be maximum, etc. So we can prove this. How? Let us see. Consider a beam of rectangular section ABCD of width and depth as shown in figure. We know that shear stress on a layer JK of the beam at a distance y from the neutral axis is tau is equal to Fa y bar upon Ib. This is the generalized shear stress equation. In this, what are the different notations? Let us check. F is equal to shear force at the section. A is equal to area of the section above Y. Area of the section above Y means what? Area of the section AJKD means rectangular strip. We will find that area. Y bar is equal to distance of the shaded area from the neutral axis. Okay, Y bar is equal to distance from the shaded area from the neutral axis means CG of the strip AJKD from the neutral axis. You can see it like this. This is the Y bar. A into Y bar means multiplication of the second and third notation will give you the movement of the shaded area about the neutral axis, which will be given in mm cube. I is equal to moment of inertia of the whole section. Whole section means the whole rectangular section about its neutral axis, which is BD cube by 12, all you can know. B equal to width of the section. So these are the different notations which are used in the equation as well as in the figure. So let us move ahead and take the figure itself and find the different values. Let us see how. You can see, first of all, we are talking about strip AJKD only. So find the area of that strip. So what is the width of the area? That is B. And what is the depth of the area? Width B and depth is quite complicated. See, how much is the depth? First of all, the total depth of the rectangle is D. So half of the rectangle is D by 2. Okay, this depth is D by 2. But out of D by 2, you can see I am writing here, it is D by 2. Okay, it is D by 2. But from this D by 2, the Y should be subtracted. This Y distance should be subtracted, so we will get the remaining depth of the strip AJKD. So it is D by 2 minus Y. So area of the strip is D by 2 minus Y. And if you want to find the CG of this strip, the CG of this strip is equal to this much. Distance of CG from the JK layer is this much. Means half of D by 2 minus Y. Half of this bracket. Okay, remember this. So here it is written half of D by 2 minus Y. Means half of this bracket. Plus you can add Y to reach the neutral axis. So Y is added. So you will getting Y bar. So what is Y bar? Y bar is equal to CG of this strip from the neutral axis, means half of the depth of the strip plus Y, which will give you the distance of Y bar like this. By simplifying this, Y is as it is, D by 4, half is multiplied in the bracket minus Y by 2. So just take an LCM and we will get Y by 2 plus D by 4. 1 by 2 will be common out, then it is Y plus D by 2 in the bracket. So it is the value of Y bar and upper one is the value of area. Now we want to find shear stress at the layer. So substitute the all values in main equation. Tau is equal to Fa y bar upon Ib. Shear force F will remain as it is. Area we have calculated B into d by 2 minus y. Y bar. Y bar is equal to 1 half into y plus d by 2. 1 half into y plus d by 2 upon Ib will remain as it is. So it will be F upon 2y. F upon 2y. How this 2? This 2 is going into the denominator. Now this bracket is d by 2 plus y and this bracket is d by 2 minus y. So it will form the formula like a plus b into a minus b. So it will give the answer a square minus b square. So d by 2 square means d square by 4 minus y square, and this b width is cancelled out. So final equation of the shear stress is tau is equal to F upon 2i into d square by 4 minus y square. So this is the value of shear stress. Now let us go ahead. We see from the above equation that tau increases as the y decreases. At a point where y equal to d by 2, tau equal to 0. You can see in the previous equation, if you replace y equal to d by over here, in the previous equation, if you replace y equal to d by 2 over here, then answer of tau will be 0. Shear stress tau will be 0. It means what? At a distance y equal to d by 2 means at a y, if you stretch the y up to d by 2 means up to top layer. This is the d by 2 distance. Then the tau becomes 0. Means shear stress at this point is 0. You can see at this point the shear stress is 0. Similarly, if you get y equal to d by 2 up to bottom layer, this is also d by 2, then the shear stress will become 0 at this layer. This is the shear stress 0. And at the neutral axis, y equal to 0. So if you replace y equal to 0 over here, then the remaining value will give the maximum shear stress. So at the neutral axis, tau will be maximum at this layer. Okay, hope you can understand the phenomena. So substitute y equal to 0 and I equal to bd cube by 12 for the rectangular section, we will get the maximum value of the shear stress. So tau max is equal to F as it is upon 2b. So 2i. So 2 as it is, I equal to bd cube by 12. Okay, here it is d cube by 12 into d square by 4 and y is replaced by 0. So d square by 4 minus y square where y equal to 0. So final answer will be getting by simplification d cube d square will be cancelled out. 1d remains as it is. 2 6 are 12. 6 upper side 2 by 3 is the cancellation. 3 by 2 is the cancellation. So final answer will give you 3 by 2 f by bd. So 3 by 2 means 1.5 and f by bd. Now what is f by bd? F by bd, b into d means area of the rectangle. So F by BD will give you F upon area means shear stress. Force upon area is known as shear stress, which is the value of average shear stress. Total force upon total area of the rectangle, which will give you the average shear stress. So final equation is 1.5 times tau average. So what we are getting? We are getting this tau maximum is equal to 1.5 times tau average. So tau maximum is equal to 1.5 times F upon area B into D for the rectangular section. So this is basically the shear stress distribution diagram for the rectangular section only. So must remember some values at for the rectangular section. At the top and bottom the shear stress is always 0, and at the centroidal axis means at the neutral axis the shear stress is maximum for this rectangular section. Let us now go ahead and check one numerical also, so that our picture is very clear. What is given in the data, you can see in the 16.1 example. What is given? A wooden beam 100 mm wide, 250 mm deep and 3 meter long. So it is 100 mm wide, 250 mm deep and 3 meter long, which is not required over here. Uniformly distributed load is subjected on the beam 40 kN per meter. Determine the maximum shear stress, means we have to find tau. Sketch the variation of the shear stress along the depth of the section. So this is the sketch. But at the top and bottom the value of shear stress is always 0. Now this span 3 meter means 3 meter into, here it is multiplication, 3 meter into 10 raised to 3 mm. Width is 100 mm, depth is 250 mm. And uniformly distributed load W is equal to 40 kN per meter. So it will be 40 Newton per mm. Now our target is shear force because we need the shear force F in the required equation. So whenever the UDL is given, remember this, whenever the UDL is given on the span of the beam, no other load is acting, then the shear force is given by WL by 2. You can find this by method of support reaction also, WL by 2. So it is 40 into 3 into 10 raised to 3 by 2 Newton. So answer will be 60 into 10 raised to 3 Newton, and the area of the beam is A equal to B into D means 100 into 250, 25,000 mm square. Replace all the values in the generalized equation. You will get tau average equal to F by A, 60 into 10 raised to 3 by 25,000, 2.4 Newton per mm square. So it is 2.4 megapascal. Now tau maximum is equal to 1.5 times tau average. So you will get the required value 3.6 megapascal as per the equation. So friends, here is the topic of rectangular section to find the shear stress. We will discuss the next topic in the next lecture. Till then, revise these values. We will meet